Science 10. We're here in a very particular way. We're taking a pair of individuals, one of them is a pair. So it's like a binary star with the second companion star going around. And Richard Feynman is being paired with Stephen Hawking and Roger Penrose. And for Penrose and Hawking, they did a debate at Cambridge University in England, and we're taking the record of their debate, the nature of space and time. And that particular series was over a 6-month period of time. Each month, one of them got to do a presentation, and the following month, the other got to do a presentation. Then they had rebuttals, and then they had critiques and conclusions. So it was a debate over 6 months. One of the Feynman is that he, like Einstein, was always outside of the mix. He was from Far Rockaway in New York City, and he literally grew up on not only on the edge of the city and the county and the state, but on the edge of America, and he was always comfortable being outside the rim where everybody else was. And he was an extraordinary character. He was finally accepted to go to MIT and study physics. And he did so well there that he was finally accepted to go to graduate school at Princeton. And when he arrived at Princeton, the dean at the time was named Professor Eisenhardt. And at the welcoming tea, the wife of the dean, Mrs. Eisenhardt, was going around to the different people and asking them, and she came to Feynman and said, "Would you like cream or lemon in your tea?" And he said, "Both," absent-mindedly. And her comment was, "Surely you're joking, Mr. Feynman." And one of his most famous books is entitled, "Surely You're Joking, Mr. Feynman." He writes of himself, "I don't believe I can really do without teaching. The reason is I have to have something so that when I don't have any ideas and I'm not getting anywhere, I can say to myself, at least I'm living, at least I'm doing something, I'm making some contribution. It's just psychological." When I was at Princeton in the 1940s, I could see what happened to those great minds at the Institute of Advanced Study, who had been specially selected for the tremendous brains and were now given this opportunity to sit in this lovely house by the woods there with no classes to teach, with no obligations whatsoever. These poor bastards could now sit and think clearly all by themselves, okay? So they don't get an idea for a while. They have every opportunity to do so. And they're not getting any ideas. I believe that in a situation like this, a kind of guilt or depression worms inside of you, and you begin to worry about not getting ideas, and nothing happens. Still no ideas come. Nothing happens because there's not enough real activity and challenge. You're not in contact with experimental guys. You don't have to think how to answer questions from the students. Nothing is any thinking process. There are moments where everything is going good and you've got wonderful ideas. Teaching is an interruption. And so it's the greatest pain in the neck in the world. And then there are the longer periods of time when not much is coming to you, you're not getting ideas, and if you do nothing at all, it drives you nuts. You can't even say, I'm teaching my class. And it goes on like this. In 1973, he received international award, the Niels Bohr Gold Medal, and we took Niels Bohr and Einstein as our first pair. We always take 3 sets of pairs and put them into an alignment which we allow to curve, so that it's not a straight line like croquet mallets, but rather it bends. And when it bends like this, it changes the way in which the crystalline structure of the mind reads out. In crystallography, if you have a crystal which you're feeding X-rays into, and you do X-ray crystallography, you will get a readout that sometimes there are blotches in a line, and yet there are some times when you are able to see that it's a continuous line. The difference is this, that if you do a crystal face along its edge, the readout will be intermittent spots. If you have the bend of the crystal, you will get a readout which is continuous. This is because of a deep reality that is in the nature of existence. All existence is precise because it is separated by articulate gaps of no things. These particulars are called quanta. If existence was continuous, there would be no quanta, there would be no way for the energy that is cinched into polarity to have a form which is stable, not stable static, but stable in terms of the energy frequency of its iteration, of its reoccurrence billions of times per time unit, so that it is there because its exact quanta of energy registry in its polarity reoccurs in that energy. And each iota, literally, of anything has its physical registry. The discovery of this in 1900 by a German physicist named Max Planck measured to almost the nth degree the constant of how this separation works between any quanta, no matter what they are, and Planck's constant H was one of the mathematical symbols that ushered in the 20th century with a whole new outlook, and one of the first people to be able to understand how to use that symbol in a new language was Einstein, with the special theory of relativity, and finally the development by Rutherford and Bohr of their discrete quantum atom, and by the mid-1920s, everyone was off and running with a whole new world. The difficulty was that the baggage that was being carried around was an extraordinary baggage of having been used to a story of the world for several thousands of years that did not take into consideration the quantization of existence of actuality, which was considered on the other side of that, on the other hand of that, as something stable. If something exists, it's stable. Whereas the fact is, if something exists, it's vibronically calibrated to re-emerge exactly and precisely in an energy frequency that's a registry of detail to any extent that one would like to have. Modern science, by the late 20th century, early 21st century, has come to understand that this is a very, very peculiar state of affairs. Richard Feynman is one of those individuals who, almost more than anyone, is responsible for being able to present this. His great lecture series, this is volume 3. All 3 were collected together. Feynman died in early 1988, and his school that he was famous, world famous for decades, Caltech, republished his lectures in 1989, and this is the commemorative edition of the Feynman Lectures on Physics. They did not republish the little Caltech booklets of questions and answers, so I brought them here so that you could see that this is a very, very interesting endeavor. The difficulty that comes from this is to realize that true science is a differential field of possibility that is literally open to infinities of refinement that have a harmonic resonance with spiritual persons, with works of art, with prismatic forms like works of art. So in the introduction to the exercises, volume 3, the professor says, the present set of exercises is designed to accompany volume 3 of Feynman's physics. Like the set that goes with volume 2, it includes homework and exam problems used at Caltech during the years 1963-1964. The earlier presentations are 62 to 63, and then 63-64. Again, it was a 2-year course. Again, I have tried to arrange the problems roughly in order of difficulty within each chapter. Even more than the preceding set, this set does not represent a final effort. It must grow as the course evolves. As a matter of fact, these problems have been typed before Volume 3 was published in its final form. I hope that any discrepancies in notation, which will therefore certainly exist, will be taken as a further indication of the preliminary nature of these problems. About 3/4 of the problems were written up by Feynman. He put in the exercises and the answers before the volume was published because he was constantly revising in such a way that there was a retrospective quality to his sense of order, which came out of his work, and his work got triggered immediately upon entering into Princeton. He was used to MIT, which was a very professional engineering university right next to Harvard. He was interested in atomic physics and the math associated with problems of that. And at MIT, the huge cyclotron area was spit and polish, beautifully organized, massive science, lots of funding. And when he got to Princeton, right away, before he went to the tea luncheon, he asked, where is the cyclotron of Princeton? I want to go and see it. And he walked into the room and he said it was a discovery for him. He said it looked like my laboratory at home, not like a big university laboratory. Everyone was tinkering. It was a mess. Things were connected or not connected. It seemed like everything was more in chaos than in order. He said I felt at home immediately because these guys were toying and tinkering to try to discover what's going on, not to prove what they thought they knew was going on. He said, I loved it. And his major professor there, John A. Wheeler, in fact, Wheeler's autobiography is called At Home in the Universe. And as soon as you open Wheeler's biography, you will find the Nine Muses that we talked about a couple of weeks ago. The Nine Muses are a resonant set of creative intuition that all of the aspects that they present in their mythic character is a creative set, and that the creative set is kept into its harmonic by a 10th mythological figure who is Apollo. And Apollo, of course, is the god of art. The mythological god of art, in the sense that he does not make the individual arts, but he keeps the harmonic of creativity so that it is a resonant set that can expand indefinitely. The Nine Muses, I've put their names in the notes, and I'll put Wheeler's Nine Muses in this. Wheeler, by the way, is still alive. He's almost 100 years old. One of the really great physicists of all time. He spent most of his life with the problem of gravitation. And when we began science with the book on Einstein's Outrageous Legacy by Kip Thorne, the standard textbook for 40 years on gravitation is by Johnny Wheeler and Kip Thorne and another professor at Caltech. Feynman learned right away from Wheeler that you have to put yourself in the excitement of doing science and the excitement of the artistic freedom to be able to create your understanding of what's going on in terms of yourself, your creative person, not in terms of something determined by your job, your credentials, the expectations, the job descriptions, but that the source of the artistic person is in the character who does the experiencing. And if the character who does the experiencing is freed by the creative artistic person, now the correlation is that that artistic personage of yours, free to create, free to participate in the art of finding out and doing, that mythic character now is jumped over the symbolic self, which is mentally ordered, and enters into a future flung quality where you're at home in the universe. Because now it isn't that your character is just in between your body and your mind, but that your character is free to spring over the limitations of the body, the prescriptions of the mind, and to find a resonance with the cosmos. Because it is the artist who is able to pull his character through the symbolic mind, because he has made the symbolic mind transparent enough to pull the character through and free that character in a completely new field. Existence occurs iteratively, yes, of course, vibronically, but it occurs in the field of nature. But there is another field that complements the field of nature, and that's the field of consciousness. And when you pull the mythic character of your experience through a transparent symbol mind into the field of differential consciousness, you now are free to roam in what is called Theoria Theory. We call it vision. The ancient word in Greek, theoria, actually translates specifically as contemplation. It means that you have taken yourself out of the limitations of the body and the prescriptions of the mind and are now free to have your experiment with your experience be open-ended. Because in vision, in differential consciousness, the binary that is operative as an operator of structuring, of engendering processes, is not the 0 and 1 of the natural cycle and the existential and the mental. The binary is 0 and infinity. And in fact, one of the problems that Feynman was able to deal with successfully was the problem that came up again and again from the mid-1920s all the way through until Feynman in the late 1940s began to understand. The problem that came up again and again was the problem of infinities always showing up in the math. That the results were saying mathematically that if you do these experiments right, you will get infinities. And so the problem was obviated in the 1930s and 1940s by a process of saying, we're going to do the best approximation of what we can come up with in terms of classical physics. Then we're going to apply a statistical mechanics sieve to this and find out what is the best possible out of a whole number of these best possibles. And instead of getting infinities, we will use that result and we will call that process then the experimental data gives us such and such as so a probability, and the infinities will fit into that probability curve if we go through a process of filtering it. Now, if we want to get the math so that the math is right, we will take the filtered out of the experimental data and we will renormalize it so that it's back into the mathematical world. This assumes that mathematics is akin to dreams and fantasy rather than the other way around. The other way around is that the math is an art form. It is a language of reality. It is a poetic that expresses exactly what is so, and when the infinities show up, it means that you've got the right answers. Because they do involve infinities all the time, because it's a part of the binary of differential consciousness, to be able to deal with an open mind in an open universe called the cosmos. One great comment on it one time in his Nobel Prize speech in 1954, William Faulkner said, "The problem with the world for man is that it's not finished yet." A good thing, because man's not finished yet either. And so he's at home in this creative, ongoing experiment with opening up into infinities. This quality of Feynman was there when he received the Niels Bohr medal. The Niels Bohr medal was initiated in 1955 when Niels Bohr was 70. His home city of Copenhagen honored him with a medal, and every 3 years they would have a very, very famous physicist, somebody who had done something not just in physics, but had taken physics out of its limitations and put it into a fresher world perspective. Bohr, as we mentioned, was world famous for his capacities to constantly bring a whole extended family of geniuses, mostly young men, who were not just the smartest guys in their class or in their city or in their country, but were some of the smartest guys of all time. And to make a home for a dozen or so of these guys so that they felt they were in a community with a papa who wasn't lording it over them, but was like them. He was interested in pursuing all the things that they're interested in pursuing all the time. And so the creativity of the extended family of Niels Bohr is one of the great stories of the 20th century. So they presented the medal. The Queen of Denmark did the actual presenting, but the presenter of why Feynman was one of Niels Bohr's 5 sons, Agi Bohr. And Agi said, Your Majesty, Your Royal Highness, Mr. Chairman, ladies and gentlemen, it is a privilege to present to you Professor Richard Feynman, who has been designated to receive the Niels Bohr Gold Medal of the Danish Engineering Society. To motivate this choice is not a difficult task because of the many outstanding achievements of Professor Feynman, but it is difficult in a few remarks properly to convey the scope of his contribution and the impact of his work and personality. Now, I'll give you a little more, but you need to understand this is a cosmic impact. The people that we are constantly taking all the way through our learning are not an impact like a force hitting something, but an impact in that the whole frame of reference that got stuck at being where it was not only moved, but dissolved. So that there was no longer the need to have a frame of reference exclusively, that one could have the living cinemascope of nature and consciousness without having to have frames of reference. You could have frames of reference if you wanted, but you would use them as a tool, not as an ordering principle and not as an orientation. Well, one of my friends in the San Francisco Renaissance was Emmett Grogan. One of his autobiographies is called A Life Played for Keeps. And when he was younger, he was in northern Italy, and he was a cameraman for Michelangelo Antonioni, the great film director. And he said Antonioni used to carry around a little slide, one of these square slides, but there was no picture in the slide, it was just the open frame. And he would constantly be holding up that unpictured slide, and as he would look, he would not look to see what filled the frame, but he was looking to see that when you moved the frame in various free-form ways, what morphed in the camera. And this is exactly the way that contemporary science got out of its stuck frame of reference, to realize that when you use your way of looking at something in a creative sweep, you do not get the lines of information that are tabulated in little pigeonholes that then you think you got something. What you get the other way is you get a teaser that the production to come has never been seen before, and so you better be wide open because no one knows what this is going to be. So Agi Bohr says, Richard, or Dick Feynman, as he is known among his colleagues, belongs to the generation of physicists who were beginning their work in science at the time of the Second World War. Among the fundamental problems facing physics at that time were the deep-rooted difficulties encountered in the description of the elementary particle. Feynman graduated from Princeton in 1942, and right away, because Wheeler was involved in the Manhattan Project, Feynman was sent as the youngest member of the Los Alamos group to build the atomic bomb. And when he arrived there, he was immediately understood, because his reputation preceded him, that he was a character. And that not only was he a character, but he was a creative artist who had to have the freedom of his spirit to work. And when he did some of the best mathematical work in the world. So they left him alone. And one of the first people to welcome him there was Robert Oppenheimer, who was an A++ intelligence and quite conscious, quite cultivated. And he recognized that Feynman is a New York City character. That's the way he is. But the way he is he's a kid in the cosmos as well. So let him play, because we need to know what happens when someone like this plays. Augie Bohr says, among the fundamental problems facing physics at that time, the Los Alamos atomic bomb group, the Manhattan Project, the creme de la creme of the mathematics and physics and engineering people in the world. Elementary particles. And one of the elementary particles that was a problem was the electron. An electron produces an electromagnetic field which may act on the electron itself, and which contributes to the total energy and mass of the electron. However, the attempts to treat this self-interaction gave meaningless answers in the form of infinite quantities, reflecting the concentration of the charge at a single point in space, which is implied by the indivisibility of elementary charge. My early associations, Augie Bohr, with Feynman go back to the war times in Los Alamos, when outside work hours he would continue his speculations involving such strange ideas as advanced interactions apparently producing effects before cause, and the notion of electrons moving backwards in time and thereby appearing as charges of opposite sign. I remember nightly discussions between Feynman and my father, Niels Bohr, and Oppenheimer, etc., who was always attracted by new ideas of a paradoxical character. He felt himself very much in sympathy with Feynman's way of thinking. So unimpressed by convention or authority, and thoroughly enjoyed Feynman's spirit and his ability to talk about the most complex or abstract phenomena in simple and vivid terms. I might add that already in those years, Feynman had acquired the reputation of a person of many talents, which included his ability to solve cryptograms almost instantly, to break codes almost beyond belief, to open safes. He cracked the Los Alamos safe to show them that nothing is safe here. Circumvent censorship. His wife, Eileen, was sick with cancer and was in a hospital down further in New Mexico. And so he was the only person who was allowed, because he would have escaped on his own, to go and visit her in the hospital and come back. And in general, to make life difficult for security officers. One of the most beautiful things about Feynman at this time, coming out after World War II was over. The atomic bomb was a success in 1945. He went for 5 years to be a professor at Cornell because a good buddy of his went to Cornell, Hans Bethe, who was one of the great physicists and scientists and mathematicians of the Los Alamos group. And so he went there to chum around with Bethe at Cornell. But slowly, he was attracted and drawn to Caltech. And it was at Caltech that Feynman spent almost most of all the rest of his life. He says, and then we'll take a little break, in the epilogue to Volume 3 of his famous course on physics, which has been used as a world standard ever since. If you take introductory physics anywhere in the world, Feynman's lectures on physics is something you're given. He says, well, I've been talking to you for 2 years, and now I'm going to quit. In some ways, I would like to apologize, other ways not. I hope, in fact, I know, that 2 or 3 dozen of you have been able to follow everything with great excitement and have had a good time with it. But I also know that the powers of instruction are of very little efficacy except in those happy circumstances in which they are practically superfluous. If you're not with me and you get it before I say it, you don't know that you know it when I say it. So let's get tuned together, and in that harmonic, the resonance, all of them, will make sets that are workable for us. That's called prismatic form. He says here at the very end, and then we'll take a break. Finally, I may add that the main purpose of my teaching has not been to prepare you for some examination. It was not even to prepare you to serve industry or the military. I wanted most to give you some appreciation of the wonderful world and the physicist's way of looking at it, which I believe is a major part of the true culture of modern times. There are probably professors of other subjects who would object, but I believe that they're completely wrong. Perhaps you will not only have some appreciation of this culture, it is even possible you may want to join the greatest adventure that the human mind has ever begun, to be at home in the cosmos. Just take a break. Let's come back to the excitement. There is a quality of building in the 20th century that is heralded. When we look back in retrospect, we see that Planck's discovery of his the constant H in 1900, Einstein's 1905 special theory of relativity. Actually, the dividing year in the early 20th century is the year between 1910 and 1911. In 1910, for instance, you had the deaths of Mark Twain and William James. In 1911, you had the publication of the 11th edition of the Encyclopedia Britannica, which is one of the great triumphs of the world. By 1912, 1913, there was beginning to get a jittery sense in the world that resulted in World War I in 1914 right away, which was a catastrophe in terms of civilization on the planet. In Faulkner's Nobel Prize speech of 1954, he said, there's only one world war, and it has never stopped. It has constantly been going on in the vicissitudes, in the multiplication, in we can look back now by 2008 almost to see that this is in fact the case. I once gave a series on the 19th century, and it was a constant discovery. The 19th century, if you follow it in a detailed morphing, not a line of trajectory, but if you take the curve of the diffraction pattern that is brought into a continuous morphing multidimensional show, the 19th century suffered a peculiar kind of breakdown. It was not a breakdown of a break, it was a dissolving away of the certainty of existence. The confidence that forms are going to stay put where they're put. The engineering of civilization showed that this was not any longer the case. The confidence of the 18th century, of the Enlightenment so-called, was that of a precision mechanistic Newtonian universe that allowed for things to be positioned and to stay there. If something is placed somewhere firmly, if you prepare for it, it is definitely placed, it is maintained, and it is protected, it will stay there. The confidence of that evaporated in the 19th century. And the discovery of X-rays in the mid-1890s just simply showed everyone graphically there are more powers at work than we even knew about, much less understood. By the middle of the 1920s, it was apparent that we did not have a capacity to really deal with reality at all. And one of the great discoveries by 1926-27 was that there are two completely different ways to look at reality in a very highfalutin mathematical way that are incommensurate. It is not just Einstein's relativity is totally different from Bohr's quantum mechanics, but that in quantum mechanics itself there are two ways. There is Schrödinger's wave mechanics and Heisenberg's matrix algebra, and they're incommensurate. And it took a very thin, lanky British genius named Paul Dirac, usually goes by his initials. In England, people are given three initials very frequently, P.A.M. Dirac. P.A.M. Dirac was Britain's outstanding theoretical physicist in the 20th century, and certainly one of the world's greatest physicists over all time. This is true. He distinguished himself while still a research student at the University of Cambridge, when, stimulated by an obscure aside in Heisenberg's first paper on the new quantum theory, he was led to identify a non-zero commutator, AB minus BA, for two semi-classical dynamical variables A and B with a Poisson bracket A comma B of classical dynamics, and he worked out as a research student already the math where the Q and the P, Q sub IS and P sub I, are pairs of canonically conjugate dynamical variables, pairs, for each degree of freedom. For an n-particle system, the coefficient of proportionality, lambda, having the value plus IH, where H denotes Planck's constant, H divided by 2 pi. The simplest examples of such commutators are those obtained by choosing, and then he goes on with some math that now applies to the new quantum theory. These pairs are certainly not ordinary numbers. With this beginning, Dirac saw the necessity for Q numbers, non-commutating dynamic variables in place of commuting variables of the classical theory, to which the Q numbers revert to the limit H approaches 0. He then went on to develop his quantum mechanics, the mechanics appropriate for the quantitative description of atomic systems, in terms of these Q numbers, along an impressively productive line all his own. Major works streamed forth, especially between 1925 and 1933. Dirac's papers are of seminal importance because he showed how you can not factor these two systems in together, but how there is a conscious expansion of dimension that does not rely upon identity or identification to be logical. And that one of the deepest fears in civilization, since the classical Greeks got swallowed by the classical Romans, is that there is an irrationality about something that can't be identified and you can't prove it, and that the evidence doesn't stay where it is, doesn't stay evidence, and that the judgments you've founded on the basis of that evidence that stays where it is can be trusted and applied, and especially that it involves a confidence that you are you. Whereas the math of Dirac and Schrödinger and Heisenberg and eventually Feynman, Wolfgang Pauli, showed that you are not you. None of us are an identity at all that is completely fictitious. Not only fictitious, it is a saboteur, trigger, like a secret informer who assassinates every realization that colors outside of the identification frame. You mustn't have those thoughts. Especially thoughts for which there are no definite picture images. You're becoming crazy. You're becoming irrational. You're becoming, finally, if you believe this, not only delusional, but even worse, you're becoming unreal. Whereas the math showed that if you don't open into this freedom, that is unreal. The whole idea of an identity is an unreality. And to free oneself from the blinder constraints of that is one of the first steps of maturity. And one of the most profound thresholds is to realize that theories upon which science develops itself are not in the mind. The theories are an actuality of the freedom of the differential field of consciousness. Theories are in the field of consciousness differentially, not in the integrals of the mind. And so one of the difficulties with this is, well then, how do you relate the mind to consciousness? Especially vis-a-vis and in terms of the universe. And right away, the trigger is the universe is an identifying idea in the mind and doesn't occur in the field of consciousness, and most certainly doesn't occur in reality. The universe is a mental idea. It is delusionary to think there is a universe. The field of consciousness discloses in the freedom of its creativity and remembering that all worlds are possible, and it's not a multiverse, it is a cosmos. A multiverse, right away, is a clever version of a universe. It's a brilliant idea that is still an idea in a mentality. It is unreal. There's no such critter. The only critter living in that universe is the critter who believes he is living in that universe. It is a private universe. It's what is called in American English bullshit. No wonder human beings have a difficulty not only getting along, but getting along with themselves. Getting along on a limited idea that this planet is, that this earth is, that this country is, this terrain, as if that's the boundary within which the arbitration of all values must take their identification and their correlation and their assignment, and you better get with that. All of that is not only fictive, but destructive. One could never live with freedom in any of those constraints. It is not possible. The best you can do is to make a game out of trying to optimize the problems, and then to just bury yourself in playing those games. They're called arcade games. And the current addiction to arcade games around the planet is like setting up mental opium dens for all the kids so that they will stay out of trouble and not be worried that they're not free, much less that they're not ever going to grow up and be real. The recalibration of this learning is to dissolve the nightmare of that unreality. When I began the University of Wisconsin 50 years ago in electrical engineering, I had wanted to go to MIT. I wanted to be a rocket engineer. And in 1956, my father took me to MIT to take a look at it, and I was all set to go and be a rocket engineer, but got a scholarship that paid for everything at the University of Wisconsin, was talked into the fact, taking advantage of, it's free. And in electrical engineering, it was obvious to me that there was something deeply wrong. I was studying the emissivity of molten metals in a metallurgy and mining course, and starting to read French symbolist poems, and starting to look at paintings by Matisse, starting to read James Joyce, and wondering, nobody ever told me that there are all kinds of flows, there are all kinds of plastic deformations that are really both interesting and scary. And one of the difficulties about all of this is something that one finds out when you begin to look at fundamentals. And by fundamentals, we mean modern science and modern engineering. And here's a book published first in 1953. It was published last in 1965. Dislocations in plastic flow and crystals. There's a crystalline form to almost everything as one of its phases of existence, of possibility. And for Feynman, he took one of the most difficult problems of crystallization that you could have, and that was the crystallization of the gas helium, which almost never happens. In fact, can't happen in nature. It's the only element that will not become a solid. You can cool helium gas down to 3 degrees, 3.19 degrees above absolute zero, and the gas will condense enough and finally liquefy. But you can take helium down to absolute zero, it'll still be a liquid. It goes against all common sense, all science, all understanding. But if you apply pressure, if you apply 25 atmospheres of pressure at 0 degrees, helium, liquid helium, will become a solid. It only happens in special laboratory equipment, and then for a little while you can understand that there's something very peculiar here. Helium is usually helium-4, but you can take an ionization of the atom of helium and take one of the electrons away and you get helium-3. Helium-3 liquefies in a different way from helium-4. They're not miscible. They don't mix. And the closer you get to absolute zero, and at absolute zero, liquid helium-3 acts as if liquid helium-4 is not there, as if it were a vacuum. There is a form of helium called rare form in laboratories called helium-6, but its half-life is only 0.82 seconds, so it's usually dismissed. But the problem with liquid helium is the problem mathematically. How do you relate these two liquid heliums, and what does this mean for process, for science? And Feynman is the person who addressed himself to this magnificently. When you come to understand genius like this, you have to understand that the genius refers to the spirit. In ancient wisdom, this was called, the popular name is the guardian spirit. But the original appellation, not designation, that's a label, that's an identification, but the appellation, what one calls it, was a tutelary spirit. And the classic appellation place where A++ consciousness was able to express it in such beautiful Greek as to be almost the most arcane, beautiful Greek ever written, by Plotinus. And in his Aeneas there is a treatise, which is the written transcript. He never wrote things, he spoke. And the transcript of what he said at this time is on our guardian spirit. That the guardian spirit is always an ordinal cut above where you think you are. And your tutelary spirit, your guardian spirit, is to guard you against the ignorance of believing in where you think you are, who you think you are, and to open it up so that you will continue to refine, continue to transform, continue to explore freedom. And as you continue to explore freedom and you raise your intelligence, your heartfulness, your living adventurousness, your sense of freedom, as you raise that up to higher orders that are more stable than stable, they're phases. Your guardian spirit always goes to a previous higher level and helps you climb. It's like Jacob's ladder. Where does Jacob's ladder go? It goes from ground zero into heaven. And climbing Jacob's ladder, one learns that there are a number of rungs that happen, and the top rung lets you fly free. You don't have to have more rungs. Once that set, that octave of 8 rungs on that ladder is achieved in a harmonic, you can fly off ladders forever. And the phrase in Plotinus was used by Krishnamurti several times in some of his deep contemplative presentations. Plotinus' phrase is the solitary quality of you opens into infinity and you return to heaven in its infiniteness. You don't go home so much as that you are at home. This quality of the tutelary spirit is to provide you with the wings that when you are ready to step into freedom in the cosmos, these wings are yours. You earned your wings. The saying is that people of tyranny, using their authority, clip the wings of the young so they can't fly. Like somebody mentioning earlier today, because of the turmoil of the 60s, of getting very close to understanding freedom, the 70s in education were especially to make sure that you clipped the wings of the young really good so they wouldn't want to be free. They wouldn't want to change the world. They wouldn't want to explore infinity. In fact, they just want to make money, have a nice job, have equipment, have a relationship or so for a while. And because I was there on the vanguard of that, the way that the lead came was the systems approach to learning. Everything needs to have its modular compartmentalization, and that modulars needed to fit together logically, and so you had to have a systems approach, and the person responsible for that in large way was named Simon Ramo. And he had 2 buddies, and they used the initials of their last name to make a company. The first initial of one of his friends was T, the second friend was W, and Simon Ramo put the R in the middle, TRW. They're the ones who brought the systems approach, especially into university level learning, and X'd out as useless 60s junk anything else, including all of the developments that had happened. I was there. By the way, if you get interested, the course outline has about 20 pages of the record of this, which I made a long time ago, so that you can understand. Because this was the time where the root of this learning took place in a serious way. I no more wanted to be a teacher than I finally realized I didn't want to be an electrical engineer. But something had to be done because it was chronic and it was crucial. And the intent was such that by 2007, it's apparent that everywhere in the world this is obtained, and everywhere in the world this is failing to a crisis point. It is a nightmare planet. It is full of as much unreality as it has ever had. And freedom itself is feared, as if it were really, ooh, scary. Oh, we're going to have to be free. We may have to do something ourselves. And not be ourselves, but be who knows what, with others that we can't categorize anymore. And they're going to be as they will. And it means that everything is going to have to be opened up for permission and discussion all the time. You can't take anything for granted, much less the self that you thought you were 2 seconds ago. This is a whole different, it's a recalibration of the scalar that not only gets us off the planet into the stars, but gets us out of the caged mentality that limits us as if it were a crystal that didn't do anything, that we don't understand that all crystals have dislocation, they all have plastic flow, they all have very interesting properties to them. I brought in magnetism and optics of molecular crystals. A molecular crystal is DNA in some forms. Magnetic ions in crystals. Crystals and light. There's a whole, the ferroelectricity in crystals and so forth. And all of this is ages ago. The current materia is far, far out. When you begin to look at the structure, let's say, of the crystalline forms of proteins, now you're able to, for the first time, to be able to understand the revolutionary, now we can't even say revolutionary, the completely new world that is struggling to emerge into its winged freedom. And one of the books I brought in is called Protein Folds. And one of the authors is Heinrich Bohr, who's a grandson of Niels Bohr, of the great Bohr family. And Protein Folds, if you just open it, page 246, 247, just for a moment, here's some 21st century cutting edge science. The little section is entitled Resonator-Driven Transition. We hypothesize that the phase transformation of a protein from the unfolded structure to the folded structure is initiated by excitations of long wavelength twistons on the backbone, that is the path integral, which became unstable in favor of curvature. That is to say, instead of it being like a backbone, that the path integral, the spinal column of the structure, has gone into a sinuosity, a curvature. The nature of the transition may be characterized as being catastrophic rather than entropic. By this we mean that the primary reason for the transition is not a change in entropy. The excitation of the twist mode is pumped to a higher and higher level. A resonator is responsible for this pumping of the twist mode. And now, when we're talking about twist modes, you realize that this is like an ambit of a helix. In particular, a double helix, which is the DNA, and also last week we mentioned Roger Penrose's twisters. That Penrose's twister diagrams and Feynman's diagrams are early attempts at a new differential conscious language of mathematics, to take it out of the heritage of 2,500 years of numeration from Pythagoras to now, by benefiting from what it was able to teach and deliver, and to put it into a new language. But the Feynman diagrams, the Penrose twister diagrams, are like the hieroglyphics of a new form of language that hasn't matured yet. And the poetic that is being used here is a transform beyond the hieroglyphics into a discursive demotic that can be spoken now with creative consciousness, even as you're speaking, so that spontaneously you learn while you're saying. And it sounds a little Zen, and it's very Zen. We're going to come back next week to some of these aspects, but I thought I would just show you, just for a moment, part of the genius of Feynman. liquid helium became an extraordinary, interesting phenomenon. This book is called Liquid Helium, published by Cambridge University Press in 1959 by professor of physics at the University of Pennsylvania, past fellow of Trinity College, Cambridge. And right away, in the preface, the liquid helium problem can be conveniently divided into two parts, a problem in statistical mechanics and a problem in hydrodynamics. The problem in statistical mechanics is essentially a many-body problem. A guide to Feynman diagrams in the many-body problem. Diagrammatica, the path to Feynman diagrams. Cambridge lecture notes in physics, just a few years ago. Two kinds of problems: statistical, dynamical. The problem in statistical mechanics is essentially a many-body problem in which the interactions between the atoms cannot be ignored, and the symmetry of wave functions plays a dominant role, because it's the symmetry and the wave functions that does the combing. In the statistical, it isn't that they're combed, but that they're distributed and averaged out to give the best approximation. An analogous situation is encountered in heavy nuclei and has received so much attention in recent years that is very close to being solved. This is 1959. In the case of liquid helium-4, Landau, a physicist of great renown, has proposed a scheme of elementary excitations, or a spectrum of energy levels, which is able to explain the thermodynamic properties, and Feynman has developed a wave function which gives this scheme of excitations. We are therefore far advanced in our understanding of thermodynamic nature of the liquid. And although it is still necessary to justify our ideas by a rigorous solution of the wave mechanics of a large number of interacting helium atoms, trillions at a time, there is every indication that such a solution will be forthcoming. On the other hand, the detailed behavior of the liquid in the immediate vicinity of the lambda point is still not understood, and the indications are that some very difficult mathematical problems are involved, but that their solution will lead to a better understanding of cooperative phenomena in general. One of the most difficult things is, how does a photon make acquaintance with an electron? How do they get to know each other? And one of the really puzzling difficulties was, how does this electron meet this electron in such a way that they become interacted? And it was Feynman in the math who was able to resolve something that couldn't physically be seen for a long time, that two electrons colliding together, one of them gives up a photon instantly, and the other absorbs that photon instantly. And so there's like a valence between those electrons, which then allow them to have the same energy shell in an atomic structure, and that the electrons in an atom arrange themselves literally in these energy level shells, and that each of these shells has a certain quota in its set, and when it fills up, you jump to a new shell. And that they go in a structure of periodicity. And there are whole developments of the periodic table and the polar arrangements of atoms and of atomic elements, and the periodicity of whole blocks of elements. And one of the interesting parts of it is that when you get to very complex atoms like uranium, or even transuranium elements that are made further actinides like newtonium and neptunium and plutonium and berkelium, californium, curium, americum, that the shells begin to show that they don't grow at the end, they emerge out of the center. If there are new orders to be had, they begin at the center and go out. You'll have 8, then you'll have 16, and you'll have 32, but you'll jump down and you'll have 8, a pair of 16s, a pair of 32s, and so forth. So that really heavy complex elements have this concentric targetness of their origin out of the fullness of the vacuum, which is so full that they can emerge trillions of time per time unit all the time exactly as they are, but they arrange themselves in such a way that there's an articulation of carrying the remembrance of some of the zeroness out of which they came with them, and that's what allows for the zeros in between the quanta. No matter how tightly you pack them, there's always going to be some zeroness articulating them. Otherwise, you don't have anything. So if you learn to carry your zeros with you creatively, you can be extraordinarily precise in everything, including recognizing yourself to have infinite possibilities. And that the person you're talking to has that as well. And that a real conversation is a chat within total freedom. Let's have a break till next week.